So everybody here is taking calculus right now, but what exactly is calculus to you? I don't want you to think of calculus as just a name of a course that you take during your first year as engineering students. There is actually a long history behind this word, calculus. Today I'm going to start by giving you a brief history of that. So why don't we start with the old definition of this word? Calculus is actually a Latin word and it was used long time ago in ancient Rome. So let's make a note on that right here. Calculus was used in ancient Rome. Ancient Rome. When was that? Around 2000 years ago. So around 2000 years ago. And what was the meaning back then? Back then, the meaning was quite different from what we have today. Back then, calculus meant a pebble. So I'm going to write it down right here, a pebble. Just in case you don't know what a pebble is, it's a small stone, really small stone. A small stone. If you have lots of them, you call them calculi. Like in this picture, you have lots of small stones. They are called calculi. The plural form of calculus. If you only have one of them, you call it a calculus. Now, it's kind of strange, isn't it? How could a word that meant a small stone in ancient time become the name of the course that we are taking right now? Well, here's the story. Back then, Roman people used pebbles for counting. Alright, so pebble lead to counting. So they used pebbles for counting. Counting what? Counting numbers of items they had, counting the distance they traveled, and later on, this counting evolved into calculation with the technology, with more knowledge. Counting becomes calculation. So counting evolved to calculation. And as you know, calculation is one of the most important parts in mathematics. So calculation, very important for math. And there you go, you see the flow, starting from just pebbles, and they lead to become something in math. So what about the modern definition? The course that we are taking right now is called calculus, but actually that is just a short form of a full name, and that full name is infinitesimal calculus. So let's write that down again. So the course that we are taking right now, short for calculus, is actually for infinitesimal calculus. Infinitesimal calculus. Okay, so what is the meaning of this infinitesimal calculus? First of all, let's talk about this calculus. Right now, we know that calculus is related to calculation. So this is about calculation, about something infinitesimal, and that word means something that is extremely small and infinitely many. Okay, so let's write the definition of this infinitesimal calculus. It means calculation of extremely small and infinitely many quantities. Of extremely small and infinitely many quantities. Okay, so we are talking about something that is really small and lots of them, infinitely many. Okay, you know, we have all these tiny pieces, lots and lots of them, and you string them together, you connect them together, they become a string of continuity. So with these tiny pieces, it becomes a string of continuity. So this leads to string of continuity. it's like you connect all the dots and in the end it becomes a line, something like that. So the string of continuity is the concept of something being continuous. Okay, so I'm going to write down right here. String of continuity leads to the idea of something being continuous. All right. So, and in the end, this leads to the modern definition of calculus. So, modern definition of calculus is about the branch of mathematics that studies quantities that change continuously. So, here's the key word. What about I write it in black? So, in the end, this is the real definition of the real modern definition of calculus. Branch of math. Branch of math that studies quantities that change continuously. Quantities that change. Okay, let me fix this. That change continuously. Okay, the key word is right here. Change continuously, constantly changing. All right. So in other words, this is the math that studies all things that change. Okay. So right here, study all things that change. Once again, the key word is change, and it has to be continuous. Okay, now let's move to the branches of calculus. So we are talking about the infinitesimal calculus. From now on, I'm going to call it just calculus. First of all, we have two branches of that. First is differential calculus. So I'm going to write down right here. I'm sorry about the space. So first of all, we have the first branch of the modern definition of calculus, and that is differential calculus. So what about I put it right here? First, differential. Okay, calculus. And for the differential calculus, we study the rates of change, slopes of the graph, and as you know, this is related to the differentiation that we are going to learn in a few weeks. Okay, and the second branch for the calculus is the integral calculus. Second branch is integral, and that has something to do with the accumulation of quantities. For example, area between curves or volumes between surfaces. And we are going to study about that after the midterm exam. And these two sub-branches, differential and integrals, are related by the fundamental theorem of calculus. And we are going to see this connection right at the end before we take the midterm. All right. So these two combined together, we get this modern definition of calculus: study of all things that change continuously. Okay. Now let's move to who invented calculus. All right. Who is the father of calculus? Actually, there are two mathematicians who are considered as fathers of calculus. The first one is Sir Isaac Newton. So let's write that down. I have the picture right here. So this is Sir Isaac Newton. Okay, Newton. And not just him, we have another mathematician, and that person is Gottfried Leibniz, the second picture. Okay, Leibniz. Okay, we have two fathers, but they did not share the same work, nor the same team. They are not in the same team. It was believed that they developed their own variant of calculus independently at around the same time. Leibniz published his work on calculus first in 1684. So Leibniz published his work on calculus in 1684, but Newton published his work a little bit later, 3 years later in 1687. So Newton in 1687. So technically, it's like Leibniz should be considered as the father, as the inventor of calculus. But it turns out that when it comes to starting the work, Newton started his work before Leibniz. Newton claimed that he started his work in 1666. All right. So he claimed that he started his work in started. Okay. Started in 1666. But Leibniz started his work in 1674. Okay. Leibniz started in 1674. Okay, let me fix this. 1674. So it's like, let me write this, publish, and this published. So one person started his work first, but the other person published his work first, and there was actually a major controversy between them for years in early 1700s on who should claim this accomplishment about being the inventor of calculus. Okay, but in the end, we honored both of them as the inventors of modern calculus because it has been proved that they didn't actually copy each other's work. They just developed their work independently, but it turns out to be happen at around the same time. All right, so at this point, you know the definition, old definition of calculus. You know the modern definition of calculus. You know who invented calculus. And let's talk about why do we need to take calculus. As you know, as I told you, calculus, for the modern definition, it meant study of all things that change. Anything that change continuously can be explained by knowing calculus. And of course, this idea is present in various fields in engineering. Like if you want to know, understand thermodynamics. As you can see here in thermodynamics, we have the change in energy leads to the transfer of heat from one medium to another medium, and in the end, we have the change in temperature. So in order to understand thermodynamics, you need calculus. So that is the first branch, just example of why you need calculus. What about aerodynamics? Anything change in this picture? Well, first of all, the position of the plane change in the space, right? Plane moves, and in the end, it causes a relative speed between the plane and the air mass. And the speed of the air mass can be considered as wind speed. And when you have wind speed and it passes through the surface of the wings, it causes the pressure on the surface of the wings. And by the design of the wings, the speed of the wind on the top surface is going to be faster than the speed of the wind on the bottom surface. And that caused the difference in pressure between the top surface and the bottom surface. And in the end, you have the lifting force that lift up the plane. What about in electromagnetic? What changes here? So by the way, the key word that I want to stress is the word change. And also it has to be continuous. Okay, in electromagnetic, you are going to spin the generator. And by spinning it, you are going to experience the change in magnetic flux. And the change in magnetic flux is going to cause the electron to move. And in the end, you have the electricity. So that is the basic idea of how generator work. And this later on can be explained by using the Maxwell equations. And in order for you to understand that, you need calculus. And the last branch that I have right here as an example is the mechanics of machineries. So you have all these parts and they move in the space together during the operation. So you have the dynamics right here. So this can be explained by calculus too. So overall, when it comes to changing, so you can link the change right here to anything that has dynamics, which is opposite of static. Static is not moving, but if something is changing position or change its value, you suddenly have the dynamics. And the dynamics is everywhere in engineering field. And that's why you need to know about calculus, and that is the first math you need in your first year. Okay, so why don't we move to the first topic of calculus, and that is function. I know that most of you have learned about functions long time ago, maybe in your first or second year in high school. And functions seems like a topic that is too basic to talk about here. But I have to include it because functions may not be as simple and straightforward as you expected. So I'm gonna start with the most basic thing of functions, the definition of functions. What are they? What are functions? Let's find out. So let me ask you this question. What is a function to you exactly? If someone comes up to you and asks you, what is a function? How are you going to answer this to her or to him? So what is a function? This seems like a simple question, right? But I don't think it's that easy to answer. So what is a function? At this point, some of you may have some ideas, and some of you may say that a function is a graph. Okay, so let's put that idea down. Function is a graph. Since I am not sure if this is correct, so I'm going to put a question mark right here. Maybe. Functions may be a graph. Alright, that is the first idea. What about other ideas? Some of you may say that no, function is not a graph. Every time I see a function, I see this, f with parentheses of x. So you say that, hey, no, function is fx. So let's put that down too. Alright, functions is this, f parenthesis and x. And I'm not positive about this either, so I'm going to put a question mark right here. But I'm going to say that they are related. Functions can be graphs, functions can be fx, but not always. Not always true. So please write this down. Okay? Not always true. Under some conditions, functions can be graphs. Under some conditions, functions can be fx. But in some other conditions, functions may not be a graph. Okay? And some functions may not be expressed as fx. So that depends on the situation and the condition. Not always, right? Keep this in mind. Not always true. Okay, so today I'm going to give you the idea, a new idea of something that is being a function. So from now on, I want you to look at a function this way. A function is not a graph, not always. Function is not always fx, but function is a transformation. That is the new idea of today. Function is a transformation. So let's write that down. I think this is very important, so I'm going to put this on the left-hand side with the box. Okay, function from now on is a transformation to everyone here. Function equal to transformation. Okay, let's put a box with some stars. Okay, very important. Transformation is about changing something into something else. Changing A to B, changing C to D. Alright, so function is about changing something into something else. So let's take a look at this illustration right here. Let's assume that this box in the middle is a function. So I'm gonna say that this is a function. And its job is to change something into something else. Well, transformation, right? This is going to be a function. And for some reason, I'm going to call this function, I'm going to name it f. Big F right here. And now I'm going to perform the transformation. In order to change something into something else, I need something to begin with. So I'm going to start with the input of this transformation. So what about I start with x? Okay, x as input. And this x gets fed into this function. This function is like a factory. Alright, gets fed here, and this is considered to be input. Alright, now after passing through this function, it's going to become something else, transform into something else. So x transforms by this function into its image, its product. It becomes fx. Alright, so this fx here is like the product of x, image of x. So let's write that down. This is the output of the function, and it can be considered as the image of x or the product of x, image of x. Okay, there you go. That is the idea, changing x into its own image. That is the idea of function. Now, what about we try an example right here? What about we put an expression into this fx? What about I pick this fx equal to x plus 2. You can pick something else, like you can pick fx equal to x squared, or fx equal to sine x. That's up to you, but I'm gonna stick with this one. It's basic and it's simple to show to you. Okay, so this one is x plus 2. So let's put some numbers in. Now for the input, I can assign some values to this x. I have the freedom to do that. So what about I assign x to be equal to 1? Okay, let's start with this. X starts with value of 1. Okay, x equal to 1 as the input. And now x equal to 1 gets fed through this function to this transformation. It becomes the image of x equal to 1. So image of x equal to 1. And it's going to be equal to, let's put 1 into this expression. It's going to be 1 plus 2, and that's equal to 3. So there you go. Starting with this input x equal to 1, and we get the output, the image of x equal to 1 as 3. And x doesn't have to be 1. We have the freedom to choose anything as long as it doesn't cause any problem. So what about I choose x equal to 2? Let's see what happens. X equal to 2, of course, same thing, transformed into its own image. Image of x equal to 2 equal to, well, 2 plus 2, we get 4. And if we keep going, we have x equal to 3, and same thing, transformed into f of 3, and that's equal to 5. So what you see right here is transformation. Changing x values into something else. So how is this going to create a graph? Well, what we see right now is just changing something into something else. So let's try to create a graph out of this. At this point, we have x value on the left hand side. All right, x, all these x. And then we have the image on the right hand side, all these things. But then we can assign the image value into another variable, and we are going to assign it to y. Alright, so what about I assign this 3 to y? Okay, same thing with 4 to y and 5 to y. Now we have x and y, and we are ready to plot it. So let's do that really quickly on the right hand side. So let's have this y-axis, okay, and x-axis. Let's have 1, 2, 3, 4. Okay, that should be enough. 1, 2, 3, 4, and 1, 2, 3, 4, 5. Okay, and alright, let me put this down. 1, 2, 3, 4, 5. This is y-axis, second variable, and first variable, that is the input, x. Okay, so let's take a look at the first one. First one, input value of x equal to 1 right here. Right here, x equal to 1, and the image is y equal to 3. Right here, so we have this coordinate, x equal to 1 and y equal to 3. Okay, let me use, okay, green is good. So coordinate x equal to 1 and the image value is 3. So we get this point. Okay, now next one. X equal to 2 and the image is 4. So x equal to 2 right here, going up here, and we get this image right here, this coordinate 2 and 4. Next one, x equal to 3, image is 5. So we get another point right here, 3 and 5. Alright, so these three are just some examples, but as you know, we can put any values of x in. We can put x equal to 1 million. We can put x equal to 1.23. So we have points between these points that we already have. So in the end, it becomes this straight line. Okay, let me put it this way, straight line. Alright, so not just these three, we have all the points between them and beyond them and before them. So in the end, we have this fx. So I can say that, hey, this fx is the graph of, this is the graph of fx equal to x plus 2. So we have this straight line of slope 1 crosses y-axis at y equal to 2. That's when x equal to 0. Okay? So that's how a transformation can become a graph. So we start with the transformation, and then after that we can put them together and plot the graph. Okay? So that's how we have the graph from the function. Now, what about functions not always equal to fx? Well, when it comes to the name of the function, you can name it anything you want. It doesn't have to be f. It can be g if you want. Alright, it can be h. It can be anything else. Alpha, beta, that's up to you. So what you see right here, you can put g, you can put f, h, or any other names you want. Alright, and that's why I told you that function doesn't have to be fx. It can be gx, it can be hx, anything that you want to name it. Alright, so now we have seen that function can be graph and function can have other names, but that's not the whole story. There is one important condition that you must consider here. For a graph or an expression to be a function, it must have this condition. So I'm going to put it right here on the left hand side. Very important. Spatial condition for an expression to be a function. Spatial condition for function. Okay, very important. Put some stars here. Okay, and I'm going to underline this. So this is going to be the condition that we need every time we see a function. So let's take a look here. For every function, one input can only create one output. Alright, let's write this down. One input, we are talking about the left hand side of this illustration. One input can create only one output. Okay, so one input right here leads to one output only. If in any case you witness one input leading to multiple outputs, then that is not a function. Okay? So what kind of situation is that going to happen? So let's take a look here. So oh, by the way, when it comes to function, you can assign anything. Like here you can assign x squared to fx, or you can assign sine x. That's up to you. Now we are going to talk about the situation where one input can give you multiple outputs. So let's take a look here. I'm going to need to use the space down here on the right hand side. So let's take a look at this graph right here. So we have y-axis, and this one is x-axis. And I'm going to put a graph of a parabola into these axes. Okay, so we have this parabola. Alright, something like that. Okay, this looks good enough. Parabola here is y equal to x squared. I want to check whether this is a function. So I'm going to check this condition, right? Whether one input create only one output. So let's check that. Let's check x equal to 1, x equal to 2, right? At x equal to 1, at this point, I'm going to check the output of this curve. So going up, I see only one output right here. Going up, and I see a point right here. And this happens at coordinate 1, 1. Alright? So, at this point, one input of x create one output, one value of y. So no problem. What about x equal to 2? Okay, this one, x equal to 1, and this, x equal to 2. I'm going to start at x equal to 2, and let's find the product of x equal to 2 according to y equal to x squared. So I'm going to follow this and find the point on the curve, along the curve, and I got to this point. Alright, so at this point, it happens at y equal to 4. So this is the coordinate 2, 4. Okay, this is 4 and this is 2. This is 1. So as you can see here, at x equal to 2, I get only one output of 4. One input, one output. And same thing here, 1.5, I get one output on the curve. 1 point on the curve. Same here, this point, go up, I get 1 point on the curve, no problem. 1 point on the curve, same thing here, and same here. So, for all values of x, I only get one values of y. So this satisfies the special condition, one input, one output. Alright, so you can go to this 1 and 2 right here, no problem. Oh, this is -2 and -1. So one value of x, one value of y, so I can say with confidence that this is a function. What you see right here is a function. This graph is a function. Now, let's take a look at the situation where the graph is not a function. So let's take a look at this one on the right hand side. So I'm going to put this y-axis and x-axis. Alright, and same thing, parabola, but this time it's going to be on the side. Parabola on the side, something like that, and like that. Okay, and I'm going to check whether this is a function. So what you see right here is x equal to y squared. The question is this a function? Okay, so I'm going to check that one input, one output condition. So I'm going to start with the x value right here at x equal to 1, and I'm going to try a few more, x equal to 2 and x equal to 3. Alright, now one value of x at this point, and I follow along the curve, try to find a point on the curve, and now I found one right here. Going up, and I found 1 point right here, happens at y equal to 1. Okay, y equal to 1, and that is coordinate 1, 1. But it turns out that at this same value of x, I get another point on the curve, and it's down here. Going down, and I get this point down here. This happens at y equal to -1. So there is another output here. Okay, -1, and this is at 1 and -1. So one value of input, x equal to 1, leads to two values of output. Alright, 1 and -1. Same thing here. One value of x equal to 2 leads to one value of output right here. And another one down here. So we have two of them. Again, same thing with x equal to 3. one output up here at square root 3 and down here at minus square root 3. So two outputs. So what you see right here, multiple outputs. So you can say that two outputs from one value of input, which means that this violates the special condition for a graph to be a function, which means that what you see right here, x equal to y squared, is not a function. Not function. Alright, and as you can see, some graphs are not function, and that's why I have this question mark right here. Not always. Not all the functions, not all the graphs are functions, just some of them. Okay? So I hope that it's clear to you. To conclude, function is transformation with just with one condition. One input can only create one output. That's all for function. Alright, now let's move to domain and range. And I'm sure that you have heard about these two words multiple times, but let's talk about this really quickly and let's get ourselves clear about what domain set is and range set is. So two things here, domain and range. So let's start with the domain. Okay, let's put the definition right here. Domain is the set of all values of the inputs that make sense, that doesn't create any violations. Okay, so I'm going to write here, D stands for domain, is the set of all inputs of the functions. In this case, we put x, right, of all inputs that make sense, okay, that makes sense, for the function, for fx. When we talk about making sense, it means that no violation would occur by using this x value. Underline this and explain that make sense means no violation. What kind of violations are we talking about? First one, division by 0. So when it comes to violations here, we are talking about division by 0. First one. Second one, complex number, square root of negative number. Square root of negative number. And another one, logarithm of 0 and negative number. Log of non-positive. Non-positive. Okay, so this is negative. So three things here to consider. As long as your x doesn't create this kind of violations, it's going to be in the domain set. So as long as your x doesn't create anything that is strange and undefined, yeah, you should count that x into your domain set. And now for the range, okay, let's put the definition right here. R is the set of all possible values of the image of x. Set of all possible values of the image of x, which is fx. What you see right here, this is image of x. I know that the definition I gave to you is like talking, not the definition from the book. But that's okay. If you want the definition from the book, you can look up in the book. But what I see right here is just how you understand this concept. And I just use this concept to find the domain of any functions out there. So let's try to do that. Let's use this idea. Domain is the set of all inputs that make sense, no violation. And range is the set of all possible values of the image. So let's try that in the next slide. Okay, so let's start with the first one. Should be the most simple one. Okay, so let's take a look at this. Oh, by the way, this is supposed to be fx. Alright, equal to x squared. This is a function, but then it gets assigned to the y variable later. So we have a function right here equal to x squared. And now we are supposed to find the domain of this function. So I'm going to use my own definition of domain set. I'm not using the one from the book. So what I know is that domain set is all values of x that doesn't create any violations. Alright? Division by 0, square root of negative number, and logarithm of non-positive number. So looking at this, is there any chance, any values of x that can create division by 0? Well, no, because we have x squared here. So definitely no problem with division by 0. What about square root of negative number? Of course not, because as you can see here, we don't have a square root. So x can be anything. No square root of negative number for sure. What about logarithm of non-positive number? Looking at this, we don't have log. So definitely x can be anything. And no violations can occur by the values of x. Since x can be anything, I'm going to say that x can be any real values in this case. So in this case, I can say that the domain set for this function is the set of real numbers. Okay? Or you can use the notation of interval. I can say that x can be anything from negative infinity to infinity. Alright, so that's it. Using this one idea, finding the violations and checking whether it makes sense for the function to exist. Okay, so this one, x can be anything, no problem. Now, what about the range? Range is the all possible values of the image of this. So I ask myself, looking at this one, the same one, can y be really big? Like really, really large number? Of course, y can be really large if x is really large. Can y be really small, like 0.01? Of course, yes, it can be done, because if x is really small, then y is also really small. Can y be 0? Yes, y can be 0 if x is 0. Can y be negative? Well, looking at this, it's clear right away that y cannot be negative because we have square right here. Out of this, everything will become positive. So, in the end, you know right away that the range for this, y can be anything except negative numbers. So you can answer with confidence. The range set is going to be anything from 0 to infinity. It can't be negative numbers. That's it. Alright, so that is the first example. Now let's move to the next one. Once again, this is fx equal to 1 over x. And we are going to check for the violation that can occur from the value of x. First, division by 0. Second is the square root of negative number. And last one, logarithm of non-positive. Looking at this, we have a fraction. Definitely, we are looking at the violation number 1, division by 0. And that can happen when x equal to 0. Alright, so in this case, x can be anything as long as it's not equal to 0. Can be anything except 0. So you can say that the domain set for this one is the set of real number minus the set of 0. Or you can use the interval notation starting from minus infinity to 0 with the curvy parenthesis, not including 0. Union with 0 to infinity and not including 0. Same thing. So that's it. Violation, the only thing that's possible here is division by 0, so we exclude it. What about the range? Okay, so let's check. Let's check the y value. Can y be really big? Be really large? Of course, if x is really small, y can be really large. So, large problem of y, no problem with that. Can y be really small? If x is really large, then y is going to be really small here. We are looking at the reciprocal of each other. X is large, y is small, and if x is small, y is large. So small number, no problem. Large number, no problem. Negative number, is there any problem with that? Well, you can see that y can be negative because if x is negative, y can be negative. So, negative numbers, no problem. Can y be 0? Can you find any value of x that makes y become 0? Well, it turns out that no. There is no value of x that can make y equal to 0. So that is the only value that y cannot be. So we can say that y can be anything. Negative, really small, really large, but it can't be 0. So y can be anything from negative infinity just before 0. Alright, and can be anything after 0 until positive infinity. The only thing that y can't be is 0. That's it. That's all I need. I used my own definitions to find the domain set and the range for this function. Let's move on. Okay, we have quite lots of them, but it's good practice. Okay, once again, I'm going to put everything as function of x, and function of x. So we are looking at this. And first of all, let's find the domain of this. So we see a square root. You know right away, we are looking at the violation number 2, the square root of negative number. So you can see here, x can be anything as long as it's not negative. So as long as x is positive and 0, then it's okay. So x can be 0 to infinity as long as x is not negative. That's okay. So that is the domain set for this function. What about the range of this function? So we have a square root right here. We know that the square root, the result of the square root, cannot be negative. Can the result of the square root be 0? Yes. If x is equal to 0, then y equal to 0. Can the result of square root become something that is really small? Yes. If x is small, then square root of small number is small. Can y be something really big? Of course, if x is really, really big, y is still big. So y can be anything except negative number. So we can put it this way. Range of this is going to be from 0 to infinity, anything except negative number. Alright, that's quick, right? Okay, let's move to the next one. This one. Function of x equal to square root of 4 minus x. We want to find the domain of this. Okay, so we want to find the domain of this, and right away we have this square root, and we know it's all about the second violation. The inside of the square root can't be negative. So we have this condition, 4 minus x has to be greater than or equal to 0. So we have this condition for this one, for this function to make sense. So you can move things around and you can see that we have this x less than or equal to 4. And there you go, you have the domain of this function. It's going to be any value of x as long as it's less than or equal to 4. Less than or equal to 4. So starting from 4, and everything has to be less than that. So it goes to minus infinity. That's it. That is the domain of this function. Right, and it comes from some calculation right here. Now, what about the range of this? So let's take a look here. We have the square root as the main function. Can y be really big? Let's take a look here. So when you look at this, if x is a really, really large negative number, then y is going to be really large, right? If x is like minus million, then you have this 1,000,004, so it's still big. So no problem with large value of y. Can y be really small? Yeah, if x is like 3.999, then y is going to be really small. Can y be 0? Yes, if x is 0, then y equal to 0. Now, this question, can y be negative values? As you can see, we have a square root here. it's not possible for y to be negative value. So we can answer right away. Y can be anything as long as it's greater than or equal to 0. Same as the third example. So y can be 0, and it can get really, really big. But it can't be negative values. Okay, last one for the domain and range. I speak fast, sorry about that, but this is easy stuff. You have done this before, so I'm going to try to go a little bit on the faster side here. So let's take a look here. We have this function, fx equal to square root of 1 minus x squared. And we want to find out about the domain set of this. So square root, we know right away that we have to check that the inside of this square root has to be non-negative, has to be 0 or positive. All right, so non-negative. So we have this condition for this one, 1 minus x squared, same thing as the previous one, has to be greater than or equal to 0. Right, non-negative. So move things around. We have this, okay, x squared less than or equal to 1, and this leads to x having to be in between 1 and minus 1, and there you go. You have the domain set of this function. So no violation as long as x is in between minus 1 and 1. So you have as long as x in between minus 1 and 1. There you go. So you check for the violation and you can achieve the domain set. Now, what about the range? Okay, so we have the square root. Definitely, this one has to be greater than 0 with the square root. So I know for sure that with the square root, it can't be negative. But can it get really big? Let's ask ourselves. Can this last one, the y value, can be really big? Well, let's take a look here. We have some form that is similar to the previous one, but here we have x squared right here. So in the end, this term is going to be positive, which means that it's going to get deducted always from this 1. Right? This term from behind can't be negative, so it's going to be something that is make 1 less and less. So the highest value that y can be is when this term right here becomes 0. That is the highest y can be. All right. So highest y can be is this term goes to 0, and that is y equal to 1. Okay. So that is the range set for this one. Once again, as you can see here, the main difference is that this term behind is always positive, and it gets deducted from this 1. So the highest this y can be is when this is gone, right? X equal to 0, and that's why you have the top boundary for the range set to be equal to 1. It can't go higher than that. Alright, okay, so that is it for the examples, the simple ones. Now I have some challenges for you, 2 of them. What about we do 1 or 2? Let's check whether we have enough time. I don't know how long has it passed, but what about we try to work on the first one right here. Okay, we want to find the domain of this function, and it turns, oh, by the way, this is not fx, it's supposed to be gx. As I told you, function doesn't have to be fx, it can be gx. Okay, so we have this. And we want to find the domain set of this. So once again, domain set is all value of x that makes sense, doesn't create any violations. Okay, domain, no violations. Violations, we have 1, 2, 3. Okay, division diff by 0. Square root of negative number and log of negative and 0. These kind of things you have to be aware of, to be careful. So we look at this function and we see a fraction. right? So the first thing is that we have to be careful is that the denominator of this fraction can't be 0. Okay? So violation. Okay, I'm sorry about that. Violation. Okay, this is bad. I'm sorry about the pen. Violation occurs when the denominator of this fraction becomes 0. So violation number 1 happens when x minus x square root of x plus 2 equal to 0. That is the first violation. So we are going to find out when this happens. Alright. Okay, let me take this out. Violation number 1, denominator equal to 0. Denom equal to 0. Okay, so let's solve this equation for the values of x that make this true. Okay, so let's move things around. This becomes x equal to square root of x plus 2. And we are going to square both sides. Okay, and this becomes x equal to x squared equal to x plus 2, and we have x squared minus x minus 2 equal to 0. And we do some factorization. We have this x minus 2 and x plus 1 equal to 0. And solving this, you know right away, x equal to 2 and minus 1. And that is where the violation would occur. Alright? So it would occur at x equal to 2 and x equal to minus 1. Violation. Okay, but let's not just conclude too quickly. First of all, let's check the values of x that you just solved. Some of them might not be correct. So let's take a look here. The original equation, you have x equal to square root of x plus 2. With this equation, you are required to have x that is positive. From this, x must be positive. Alright, as you can see here, x equal to square root of something. So x can't be negative. But in the end, you have this one right here, x equal to minus 1. So this is a wrong answer. You are not supposed to count this. And this wrong answer appear here because you perform the square root, and that's why you have some extra solution that does not belong there. So negative value of x shouldn't be counted here. So we only have one violation occurs at x equal to 2. Okay, so that is violation number 1. Okay, so let's keep this for now. X equal to 2, we cannot include this in our domain set. Alright, now that is not the only violation we have here. So let's take a look at the violation number 2. Okay, so violation number 1 is about the denominator equal to 0. And it turns out that we have another thing to be careful of because we have this square root right here. The inside of the square root cannot be negative. That is the violation number 2. Violation number 2. Okay, so we require x plus 2. By the way, x plus 2 must be greater than or equal to 0. Okay, and we solve this. We have x must be greater than or equal to minus 2. Alright, so now we have this second condition from the second violation. X must be greater than or equal to minus 2. And from the first violation, x can be anything except 2. Okay, so let's combine them together. 1 plus 2. So from number 2, domain set, x can be anything that is greater than minus 2. And it can go to infinity, right? but it turns out that there is one exception at x equal to 2 from the left hand side. So we have to exclude x equal to 2 from this range. So the range we have is going to stop just before 2 because x equal to 2 is a violation. So we have to exclude it. Union, another set starting from just after 2 until infinity. And there you go. We have the domain set of the first challenge problem here. Okay? And as you can see here, this one is a challenge because we have two violations to be careful of. One is the denominator. This is about the division by 0 right here. And the other one is about the square root that we have in the function. So, number 2. And when we combine them, we just take out the exceptions. And we have arrived at the final answer, this one. Okay, and what about we try another one? Alright, so I'm going to need to erase all the work that I just drew, that I just wrote right here, because I need space for the second example. Okay, so finish this, and I'm going to erase everything I have here. Okay, give me some time. All right. Okay, that is good enough. Now, for the second challenge problem, we want to find the range of this new function gx equal to x minus 2 divided by x plus 3. So we want to find all possible value of the image of x. Okay, all possible values of this function. So what do we know right here? Let's take a look here. We have this x minus 2 as the numerator and x plus 3 as the denominator. So this is numerator. I'm gonna say num, numerator, and this is denominator, denom. What about numer? Okay, and this is denom. Okay, at this point, I don't know where to begin, but what I know is that x minus 2 is always less than x plus 3. That's how I see it. I know for sure that x minus 2 is always less than x plus 3. Of course, this is same x, right? And we have minus 2 over here, and we have plus 3 over here. Of course, the right hand side is going to be greater than the left hand side always. So one thing I know right now is this condition. I'm going to put a box around this. So that is what I know. And I'm going to work on this. What about I start with the case number 1? Case 1. Let's work on this. When x, this is case when x is greater than minus 3. I have this condition in my hand, and I'm going to work on this. Case 1 is when x is greater than minus 3. Let's see what's going to happen. So we have this x minus 2 and less than x plus 3. And what I'm going to do next is to divide both sides with x plus 3. I'm going to do this. Divide both sides, x plus 3. Divide this, x plus 3. And as you can see here, I have this condition, x greater than minus 3, which means that the division that I make right here, this term, it means that x plus 3 is greater than 0, which means that the sign I have right here is going to stay this way. We don't have to flip it because the division is, this is division by a positive value. This is positive. Positive. And I make the division with positive value, so I don't need to flip the sign. Alright, so this is going to cancel and become 1. So what I have right here is that x minus 2 divided by x plus 3 is going to be less than 1. And it turns out that this x minus 2 divided by x plus 3 is equal to the function that we have. So this is g of x. So at this point, I know that the range that I have, it must be less than 1. Okay, that is the first condition. Must be less than 1. Alright, now I only consider the first case. What about the case when x is less than minus 3? Let's check on that. Oh, by the way, let me ask you, can x be equal to minus 3? Well, as you can see here, if x equal to minus 3, the denominator becomes 0 and we have the violation. So I don't need to check when x equal to minus 3. Alright? So I need to check the second case when x is less than minus 3. So what's going to happen? Okay, so in this case, x plus 3 is going to be less than 0. With this, I know this is negative. Negative, right? So I'm going to do the same thing. X minus 2, starting with the condition I have over here, x minus 2 always less than x plus 3. And I'm going to perform the division again. Divide by x plus 3. Divide by x plus 3. But in this case, x plus 3 is negative, which means that I am required to change the sign to be the other way around. Okay? So in this case, we have this instead, and this is going to get cancelled to be that. Okay, and this turns out to be equal to g of x. Alright, and let's conclude this. G of x, oh, let me do this right here. G of x greater than 1. And from this, g of x on the left hand side, g of x less than 1. So we are going to combine them together. Alright, g of x greater than 1 and g of x less than 1. Okay, from the second condition, let me write it right here. Second condition must be greater than 1. Okay, combine them. So we are going to get this range set can be anything that is less than 1 from number 1. Anything that is less than 1 minus infinity to 1. And anything that is greater than 1. Alright? So union, anything that is greater than 1 from 1 to infinity. Or you can say that this range set equal to the set of real number minus the set of 1. That is the only one exception for this image value. So that is it. In this case, you have to consider both cases in order to find the range of this function. Alright? So that is the second challenge.